Well, thank you very much indeed for inviting me to speak. It's a hard act to follow, the previous dance performance, which I thought was wonderful. And I should start with a disclaimer to say I'm not a basic scientist. My background is more in epidemiology, for many years in clinical medicine, public health. But what I'm going to try and do is to lay out the kind of big picture for you and indicate where I think that some of the basic life sciences can contribute to addressing some of the unanswered questions in the nexus between climate change and human health. So let me start by just saying a few words about the kind of evidence that we need. And I think we always need to bear in mind that what we need here is action. Ultimately, we cannot just observe the effects of climate change on health. We actually need to act in order to reduce the impacts of climate change, either by adapting to the changes that we can't prevent, or by mitigating, by cutting greenhouse gas emissions. And I also want to mention that climate change is but one of a number of planetary scale changes that we're seeing. And we know that many of the planetary boundaries that have been articulated by colleagues like the late Will Steffen, Johan Rockström and others are being exceeded. So there are multiple concurrent environmental changes that interact in ways that we don't fully understand. So a transdisciplinary understanding of the complex causes of changes in health with these multiple concurrent stressors is imperative. Assessing potential tipping points beyond which sudden state shifts may occur that pose increasing risks and often non-linear risks to health. And so that's the kind of scientific discovery end of the research, but we also need research to support and enable action. And actions would include early warning of impending threats to human health, evaluating the effects of adaptation and mitigation actions on health, monitoring progress towards nationally and internationally agreed targets, and overall enhancing transparency and accountability of decision makers. So this infographic attempts to summarize what is a complex picture, but let me just take you through it very quickly. At the top, you can see the increasing levels of carbon dioxide and the short-lived climate pollutants like methane, black carbon, lead to rising temperatures, increasing sea levels, increasing extreme weather events, and through a range of demographic, socioeconomic, and other environmental factors, these influence the magnitude and the pattern of risk to the human populations. And in the middle of the infographic, you can see the exposure pathways by which health may be affected. That's not comprehensive. Arnaud will be talking later about pandemic risk, for example. But you can see that they range from the very direct, the extreme weather effects of floods, droughts, heat stress, and so on. Air quality because of changes in allergen production, also wildfire smoke, water quality and quantity, food supply and safety, vector-borne disease distribution, vector distribution and ecology, and of course social factors. Increasing poverty because people can't work as much in some areas, probably increasing conflict, population displacement, and so on. And these are difficult to estimate, give quantitative estimates of, but they may turn out to be amongst the most important impacts. On the left here, you can see the difference between the temperatures that we would be observing, that's the orange line, if there were no human greenhouse gas emissions from human activities, and the red line shows you where we're going. We've already heard from Naki's brilliant presentation the kind of future that awaits us depending on the climate change, the decisions we make about climate change. And you can see how those lines are diverging. So we're now over 1.1 degrees global average temperature, above pre-industrial. But of course that's not homogeneous. The temperature increases differently in different parts of the planet. The land heats up faster than the oceans. Some parts of the planet, like the Arctic, for example, are heating up faster than others. And increasingly, we can attribute health effects of climate change to human-induced climate change, so not just due to natural fluctuations in climate. And the map on the right is from a recent study undertaken by a whole number of my colleagues at the school, but also many international collaborators from over 730 sites in 43 countries. And they estimated that more than a third of the total heat deaths over recent decades could be attributed to human-induced climate change. But you can also see there are big grey areas on that map. And these are the parts of the world where we don't have good data. because we don't have the data collection systems that would allow us to estimate, to look at the daily deaths in relation to changes in weather and climate. So there are big data gaps that need to be filled in, and these estimates are probably underestimates for that reason. You can see that from this slide that heat exposure has different effects on death. And this is just 4 European cities. So if we looked across the world, there'd be even greater diversity. You can see, for example, London, that sort of familiar U-shaped effect. So there's increased deaths in cold weather, but also rapidly increasing deaths in hot weather as well. Stockholm, at the top right there, different pattern, not much increase. In fact, very little increase with cold weather, probably because they are well adapted to cold temperatures, and some increase with hot weather. And then Rome and Madrid have their own patterns, more probably similar to London than to Stockholm. So the relationship between heat exposure and death rates depends not just on the temperature you're exposed to, but also the local environment, the housing stock, the social determinants of health, and other factors as well. The aging of the population, because we know that older people are more sensitive, more vulnerable to heat than younger people. But in low-income countries where you don't have good infectious disease control systems, poor health systems, then children, infants are also very much at risk. One of the other things that happen as you heat up the planet, of course, is it makes it more difficult to work. And on the right side of this slide, you see the map. It's from a paper we did some years ago with a number of colleagues, including Corinne Le Carré. And this shows you how the extreme heat expands. The extreme heat, that's the yellow area on the map. And that's the area of the planet where it'd be extremely difficult, hazardous, to work for at least a month of the year, and probably more than that, probably again conservative. And you can see how, as the temperature increases, the global average temperature, that yellow area expands. And that means that perhaps 1 billion people or more could be exposed to these temperatures, and that will make it increasingly difficult for them to work. And on the left, you can see that image. One of the vulnerable groups here, of course, are subsistence farmers. And we've been doing some work in West Africa, in the Gambia, looking at pregnant women subsistence farmers, measuring the heat exposure in the field, literally in the field, and showing that the fetal heart rate goes up in proportion to the heat stress that women are exposed to. And it goes up quite significantly at the end of a shift. And we believe that that's already showing evidence that heat is affecting the health of the fetus, and will increasingly do so in the future. But women, of course, have no choice because they have to feed their family, so they have to go out and work in these very difficult temperatures. We also know that the odds of preterm birth increase per degree increase in temperature above a particular optimum, which varies in different parts of the world. And this shows you the summary evidence from a meta-analysis of a couple of years ago. The data comes mainly from high and middle-income countries, so it doesn't include the most vulnerable populations. But what you can see is that there is an increased odds of preterm birth per degree increase in temperature above this optimum. And you can see the overall estimate is given at the bottom. So there's good reason to believe that increasing heat will increase the risks of preterm birth, possibly stillbirth, and it will have adverse effects on pregnancy, a range of pregnancy outcomes. And if it affects the health of the fetus, of course, there could be long-term effects on the prospects for children. We know also that wildfire risks are increasingly affecting our health in some parts of the world. And this is because of at least in part, because of the particles that are released when wildfires, when landscape fires take place. These particles are smaller than those in typical urban pollution. They have a higher proportion of these very, very fine particles, PM2.5, and they appear to contain more oxidative and more pro-inflammatory components. So understanding the mechanisms by which these particles are working, well, having their effect will be extremely important. And I should have also said in the previous slide that understanding the mechanisms by which extreme heat is affecting the health of the fetus and the mother, of course, is going to be important. And that's where some of the basic life sciences will come in. And you can see that after people are exposed to wildfires, all-cause mortality goes up for 3 days following the exposure. heart disease, respiratory mortality as well. And on the map just shows us where some of these extreme exposures take place. And you can see, if you can see the small print, that some of them are extraordinarily high. I mean, 200 micrograms per cubic meter, which is an extraordinarily high level of fine particle exposure. But we also know, of course, that climate change affects a range of infectious diseases, and Arno will be talking more about some of those later on. But just briefly, I've mentioned vector-borne diseases, food and waterborne diseases, and of course zoonotic diseases. And climate change can affect the pathogen, can change the viability of the pathogen, change the range of the pathogen. It can affect the disease vector, of course, mosquitoes, ticks, and so on, and affect the host as well through famine, through undernutrition, forced migration. And all of these factors act in a more or less synergistic way to increase the risk of infections. Just one example, this is the estimate of the vectorial capacity, the ability of the vector mosquito to transmit this very common viral disease, dengue. And there are two vectors here, Aedes aegypti and Aedes albopictus. And you can see that in both cases, the capacity, the vectorial capacity, has gone up in recent decades as the temperature has increased. And this means that climate change is probably contributing to the spread of dengue around the world. And of course, these mosquitoes, Aedes aegypti in particular, for example, transmit other viral infections like chikungunya, like yellow fever, and so on. Now, El Nino is a really interesting phenomenon, not just from the climatological point of view, but from the perspective of public health. And what we got interested in some years ago was the linkages between the El Nino phenomenon and public health. It's a kind of brief couple of years blast of climate warming. And of course, it's due to natural processes. We don't quite know how it's going to interact with climate change, but it's a very important stressor, which can be a kind of, if you like, a sort of population laboratory for telling us the kind of diseases and health outcomes that could be affected in the longer term by climate change. And this slide just summarizes, it's not from our work, but it's from another paper, and it shows you the relationship between the 2015-2016 El Nino and different health outcomes around the world. So you can see a range of communicable diseases like hantavirus, plague, West Nile virus in North America, chikungunya, dengue, malaria in northern Latin America and Colombia, for example. Parts of Brazil also dengue. Respiratory illness from wildfires, from greater burning of the forest. And then in East Africa, cholera, malaria, Rift Valley fever. South Asia, cholera, so it affects ocean ecosystems as well, and therefore cholera risks increase. And then in Southeast Asia, you get increased burning of forests, again, increased transmission of some viral diseases. So this gives us an indication of the kind of conditions that are affected by these relatively short-term fluctuations in climate. And I would submit to you that probably bringing together those public health researchers, climatologists, and biologists, basic scientists, to study some of the mechanisms by which these disease risks are increased could be a very useful lens, if you like, into a better understanding of how these longer-term climatic changes could affect health. As I've mentioned, we know that it's not just terrestrial systems, it's also oceans that are affected by climate, very much so, ocean acidification, for example, many other environmental factors like microplastics and so on. And there is growing interest and some evidence linking climate change, ocean, and human health. And one example of that is shown on this slide, a map which shows you the coastal waters with environmental conditions that are suitable for the transmission of Vibrio. Vibrio can be Vibrio cholerae, but this is not cholera. This is other Vibrio species. And you can see that the Baltic, for example, that yellow area, and also the Black Sea, the red area, shows you where the transmission is increased. It's for one particular day, it's August 2018, and the transmission changes very much according to the temperature and also the other environmental conditions like nitrogen and phosphorus loading as well. So again, this shows you how the health of the oceans is inextricably linked to human health. And of course, there are many other mechanisms linking them, for example, through fisheries, which are an important source of nutrition for a couple of billion people around the world. But we also know that there could be some unexpected and unpleasant surprises ahead, and one of those, of course, may be from melting permafrost. So as the permafrost melts, then organisms can be released from the permafrost. It is not known fully what the implications for human health might be, but there have been a couple of workshops, one by the Inter-Academy Partnership, also the National Academy of Sciences in the US, which have discussed the potential implications of melting permafrost for human health. And it's very clear there could be a range of pathogenic organisms like smallpox virus, Clostridium bacteria, also toxins like mercury, nuclear waste, atmospheric chemicals, persistent organic pollutants, and others that could be released as the permafrost melts. So again, this is a really important area for collaboration between basic biological sciences, epidemiology, and those who study the cryosphere. It was mentioned yesterday, of course, and we're hearing a lot more about this tomorrow, I think, the impacts of climate change on food security. The map shows you where we're going to see declines in food productivity and crop productivity, the red areas, and you can see that there are also green areas where we may see some, at least transient increases. Don't know how long they'll go on for. And of course, the tragic Ukraine war has shown us that there could be other factors that would prevent countries exporting their crops to countries that are affected particularly by climate change. So we have the kind of perfect storm, declining biodiversity, pollinator loss, reduction in fresh water availability because of the depletion of aquifers, and climate change are all impacting negatively on the food system. And on the left side of the slide, you can see what the climate models, the agricultural models, show us, which is that over the century, things get worse, those red and orange bands get bigger, and that means that crop yield, all other things being equal, will get worse. And it's not just staple crops, of course, it's also fruit and vegetables. And fruit and vegetables are so important for the prevention of cardiovascular and other non-communicable diseases. I should also emphasize it's not just the quantity of crops, it's also the nutrient quality. So as you put CO2 into the atmosphere, you reduce the micronutrient level, zinc and iron. So that will increase micronutrient deficiency. And then finally, mental health. Of course, it's not just physical health that's being affected, it's also mental health. We heard very briefly yesterday, I think somebody mentioned the concept of solastalgia, which is the distress which is caused by environmental change. So when communities are forced to relocate in the Arctic because of melting ice, then they suffer very understandably from this environmental distress, which has been labeled as solastalgia. And if you follow up people who've been exposed to floods and droughts and wildfires, follow them up for a year, you find high prevalence of depression, anxiety, and other common mental disorders. And on the right side of the slide, you can see the results of a survey a couple of years ago in the Lancet Planetary Health Journal, which showed extraordinarily high levels of climate anxiety amongst young people and adolescents. And about 45% of them, of all these different countries overall, said they were suffering from such severe anxiety about the future that it was having an impact on their functioning. So although it varied from country to country, it was common, unfortunately, in all countries. And they also, these young people, had very little faith in political leaders to address these issues in the necessary time, within the necessary ambition and time scale. So really worrying trends for mental health amongst the young, and really I think an important area for research, not just in documenting the impacts, but also trying to understand what we can do to alleviate some of those concerns. And some of the answer to that may lie in engagement with climate action, understanding the mechanisms more precisely. So what are the actions we need to take? Well, there are two types of action, aren't there? Adaptation, as I've said, to those effects that we can't prevent, and mitigation, action to reduce the emissions that cause climate change. So adaptation means more resilient healthcare systems, better disaster management, better flood protection, infrastructure upgrades, and so on. The evidence base for that is still quite weak, particularly in low and middle income countries, as shown by this paper from my colleague Pauline Schielbeek and others. She found only 2 studies were formal evaluations of climate change adaptation responses and their impacts on public health in low middle income countries. So there's kind of an inverse evidence law here, if you like. So the the populations least responsible for climate change and the most vulnerable, where we need the evidence best, are those where we have the least evidence. And that's a really important gap, I think, to fill, which will mean forging collaborations between life scientists, public health scientists, and others, particularly in low middle-income countries. And then mitigation, big opportunities there to reduce climate change, as Naki has pointed out, but also to yield big benefits for human health. Not just the benefits of reducing the risks of climate change, but also the co-benefits, as I mentioned very briefly yesterday. I'll come on to that in just a second. Just say a few words about adaptation. One example would be how to adapt to heat. And this is an infographic is taken from a paper a couple of years ago by Ollie Jay and colleagues in The Lancet. And they made the point that, of course, the health sector has an important leadership role, but it can't do it alone, because community response plans require engagement of other sectors, like urban planners, mayors, city leaders, and so on. They require integrated surveillance and early warning systems to give early warning of extreme events, but also cooling centers, distribution of potable water, ensuring that vulnerable populations like the elderly, people living in informal settlements, refugee camps, mass gatherings, are also provided with a means to adapt. So although the healthcare sector can do something, it's essential to work with urban planners, those who design buildings, and others, to understand better both the basic mechanisms by which we can protect against heat, by which we can measure this protection, and also what needs to be done to reduce exposure. And I'd like to just very briefly touch on this example of a randomized trial in Burkina Faso that is being led by our colleagues in Burkina, Ali C, and also colleagues at the University of Heidelberg, some of them shown here. And this is an interesting study because what it's trying to do is to see whether painting roofs white will actually reduce the heat burden within the homes. And the roofs can be tin roofs sometimes, or mud roofs. I can't give you the results because the study is being analyzed at the moment. But what I would say is that one of the problems with these kind of studies is the outcome variables are relatively crude, because you can't do a trial that's big enough to look at death rates. It's not really feasible. So what you need is better biomarkers of heat exposure. And I think that's something that the basic research community could collaborate on with those people doing field research. I think some of the biomarkers we hoped might work, like heat shock proteins and so on, are probably not sensitive enough to measure some of these changes. So if we could get better biomarkers of exposure to extreme heat, we could use these as surrogate outcome measures in some of these kind of public health trials, if you like. So let me move on quickly to mitigation. This slide tries to summarize what we need to do if we're going to reach a 1.5 degree world, which of course, as Naki has said, is sadly now out of reach. We still hope to keep under 2 degrees, but it's going to be a struggle, as Naki has said. So this just shows you what we need to do and what we're not doing. I won't read it all out, but I think most of it is fairly obvious to you. But the point I want to make here is that these actions can reduce greenhouse gas emissions, but they also have big co-benefits. We call them co-benefits because they're ancillary to the main purpose, which is to cut greenhouse gas emissions. But if you stop burning coal, for example, then you reduce air pollution, obviously, fine particulate air pollution, and also mercury, which comes out of coal plants. Likewise, if you stop diesel cars, then you have less particles, less NO2 from exhaust emissions. So there are many examples of those, and I'll touch upon one or two of those in my latter part of my talk. One of the problems we have at the moment is that most of the evidence is modeled. So it's very useful, it's mathematical modeling, extremely valuable in giving us some of the potential benefits that we could achieve through cleaner air, through healthier diets, through more sustainable transport systems. This slide just summarizes some of the health exposures that result from these strategies. Obviously air pollution, better physical activity, healthier diets, particularly reduced consumption of red meat, which is linked to methane, obviously, in high-consuming populations, but importantly, increased consumption of fruit and vegetables, which will be more difficult because of climate change, but nevertheless important. And then they show you the health effects on the right side here. The problem is at the moment we don't have standard methodology, and again, having better biomarkers of the effects of some of these mitigation factors would be really helpful, I think, in terms of combining some of the insights from epidemiology and public health with some of the insights from basic biology. The potential health benefits could be very large if we could realize them. This is a study we did some years ago led by our colleagues in the Max Planck Institute for Atmospheric Chemistry in Mainz, which looks at the benefit of phasing out fossil fuels and shows that there could be millions of deaths averted annually from reduced ambient air pollution, getting on for 4 million, and that's being updated at the moment. It's probably actually even larger than that. Some estimates suggest more. And those deaths are shown on the map here: China, India, Europe, North America, not so much in Africa and Latin America because they don't burn as many fossil fuels, but if they go down a high fossil fuel intensive development pathway, then they'll create more air pollution. So these are relatively near-term benefits. So these can occur within, well, certainly probably years, but some benefits occur even within weeks and months of reducing air pollution. We also know that it's not just the carbon dioxide mitigation, it's also methane, which as we very briefly mentioned yesterday, is an important, relatively short-lived climate pollutant. If you look at the climate impact over a 20-year period, it's 86 times that of CO2 per unit. And it has implications for human health. Although methane is not damaging itself, it's a precursor of ozone. And tropospheric ozone in the atmosphere is damaging to human health. So cutting methane can also benefit health, reduced respiratory diseases and so on. It also can enhance crop yields because ozone is damaging to crops as well. So big benefits there. Big benefits from increasing green space and reducing traffic in cities, not just from reduced air pollution, but also physical activity. And this is an interesting concept from our colleagues in Barcelona. And they've advocated this idea of superblocks, where you amalgamate city blocks, you prevent through traffic, you plant more trees and so on, helps to cool the city, but also reduces motor traffic. And they have indicated that if they could scale up that approach to the whole of Barcelona, they could prevent substantial adverse effects over coming years. And they've also documented the mental health benefits of green spaces, the mental and physical health benefits, as shown in the left part of the slide. And the black text shows you where there's good evidence, and the grey text shows you where there's emerging evidence. But again, I think this is a real area for collaboration between some of the basic biology and the public health epidemiology sciences, because we don't know the full mechanisms for this. Some of it could be due to reduced heat exposure, some due to changes in air pollution exposure. There are also hints that there may be changes even in microbial diversity, that those people exposed to green space may have a more diverse microbiome. So understanding the basic mechanisms of this would be, I think, extraordinarily valuable. We assume that electric vehicles are going to be beneficial to health, but it's more complex, I think, than we often think. Because if we replace fossil fuel vehicles with electric vehicles, there are obvious benefits. I mean, they're not going to be tailpipe emissions. So there won't be fine particles from tailpipes. There won't be NO2. But the tire and brake emissions, the fine particles from tires and brakes, will still be there. And some evidence suggests that these metallic and tire particles could be biologically very important. So understanding the biological mechanisms by which some of these particles have an effect will be extremely important in understanding the balance of benefits and disbenefits in changing the transport system. And some of these, this is one of the reasons why we're also looking at other strategies, which is increasing public transport, more active travel, walking and cycling, which brings, of course, physical activity benefits as well. Nature-based solutions, lots of interest in nature-based solutions at the moment. They can contribute both by promoting adaptation, as I've mentioned, cooling urban environments, but also mitigation. They lock in, they suck in carbon, if you like. So there are different types of nature-based solutions. I don't have time to go into detail. And they probably have different environmental and probably human health effects as well. Again, this is likely to be a very fruitful area for research, for applied research, but also more basic research to understand the mechanisms by which nature-based solutions can have their beneficial effects. And they may be very minimal interventions, keeping natural systems intact, moderate interventions like agroforestry, and completely new ecosystems like green roofs. But the important take-home message here is that we need to respect indigenous knowledge, because many of these natural systems are indigenous people are the custodians of many of the most biodiverse areas of the planet. And so it's really important to respect that indigenous knowledge and to integrate it as far as we can with our own scientific concepts, maintaining biological and cultural diversity. And then finally, the food system itself. I won't say very much because there's going to be lots said about it tomorrow. But the Eat Lancet Commission pointed out some years ago their recommendation of the planetary health diet, which was a bit controversial. Some people didn't like the ideas, but I found it quite compelling myself. And what they said was that if we could promote a more sustainable diet with more whole grain carbohydrates, more fruit and vegetables, nuts and seeds, reduced consumption of red meat, and dairy products in high-consuming countries, this would improve health and, of course, reduce the environmental pressures of the food system. And there's lots of potential contributions also of novel and future foods, which will be discussed tomorrow, but this slide summarizes a few of them: cultured meat, microprotein, and others. The important thing here, they do have potential to reduce water use and global warming and climate change, but it's important to evaluate each one of them because some of them may have unintended adverse consequences as well. And finally, the healthcare system itself is a major contributor. About 4 to 5% of the greenhouse gas emissions come from the healthcare system. If it was a single country, it would be the 5th largest emitter on the planet. And a lot of work is going on now to develop and build health systems which are not only able to withstand the impacts of climate change, but are also low carbon and sustainable. Much of those emissions come from the supply chain, from pharmaceuticals, medical equipment, and so on. Behavior change interventions, I won't go into detail, I'm running out of time, but just to reinforce really what others have said is that behavior change is absolutely crucial to this agenda. You cannot impose change on people. Change has to come from co-design of interventions and actions. And we have to make the sustainable choice the easy choice, because many of our behaviors are automatic behaviors. This is a useful conceptual approach that we've used, the behavior change wheel. It's not the only one. There could be many others as well. But just to really emphasize the importance of behavior change research. So let me conclude by saying that climate change has multiple effects on human health. As far as we know, most of those are largely negative. But acting on climate change, both adaptation and mitigation, can really produce major benefits for human health, both in the distant term, in terms of reducing the risk of climate change, but also in the near term, by capitalizing on the near-term co-benefits of climate action. And as the next COP approaches, COP28, there will be a health day at that COP. Unfortunately, we know that many countries are doing too little to protect health from climate change. And so this is a wake-up call, I think, for the research community to get together and really try to address some of the fundamental challenges that are preventing us from protecting and improving human health in the face of climate change. Thank you very much.